So once we understood what signals and systems are, we saw that signal analysis and system analysis are the next big portions or modules that we have to understand. So we'll start with signal analysis. So in order to analyze the signal, first we have to represent them or model them. So we'll try to see how to represent them analytically, or how is it modeled using equations. Okay, a very simple example is, now let's say I have a sinusoid. What is a sinusoid? It's something like a cosine signal. Okay, now I can model that mathematically using some equations. Okay, so I have written here some equation. As you can see here, what we have done is we have written this entire signal as a function of time. Remember, we said that a signal is nothing but a function of some independent variable, and we are fixing time as our independent variable. So throughout this course, most of our independent variable, not most, all of our independent variable will be either time or frequency. So in this case, we have taken time as the example. So time is our independent variable, and the signal is varying with respect to time. And how is it varying? It is varying as a function, and function which is given by cosine. So this is the relationship between the signal that we are observing and the independent variable time. Okay, so this is how we have modeled this signal, which means, what is modeling? A model helps you to understand everything about the signal. A model tells what are the properties, what are the characteristics of the system and the signal. Okay, so in this case, we are trying to model a particular signal, and we are saying this is the model, which means given this model, I can tell what happens to the signal at any point of time. Time is the independent variable. So if I want to know what happens to the signal at time t is equal to 5 seconds, at time t is equal to 1 hour, at time t is equal to 10 years, at time t is equal to 1 million years, then just plug in the corresponding value of time here, and this representation or this model will tell you what is the value that the signal will take for the time that you are asking for. This is what we refer to as a mathematical model or a mathematical representation. So the moment you model it, you know what happens to this completely. So another example is just t plus 3, which means the signal is nothing but adding plus 3 to the time. Okay, and if you take this signal, it is simply saying that if time is between 0 and 1, then the signal's value is 1, otherwise it is always 0. So what we are saying is, the definition of a signal, as we said earlier, is a function. And how are we capturing all the information in this function? By writing a mathematical equation, or what we call as a model, a representation. We'll just say that the function or the signal is dependent on time in this manner, and that manner is captured by this equation or this representation. Now, if we can graphically visualize this as drawing a plot where the x-axis is time and the y-axis is the signal that we are trying to visualize. So 2 cos pi t will look like this cosine function that you have here, and t plus 3, whatever is the time, as you can see, it just adds plus 3 to it. At 0 you have 4, at 2 you have 5, and so on. And this function, it is just a pulse. It's a nice rectangular pulse that you see between 0 and 1, and all other places it is 0. This is what we will say as the analytical representation or a model of a signal. Now, the next question that we can ask is, what about this time t? Should it be always positive? Can it be negative? When we are looking into example of a signal, we saw that we can graphically represent a signal in this form. So you can have the independent variable and you can have the dependent variable, right? So the dependent variable keeps changing over time. So we saw in all those examples, the time was starting at 0. Now, going forward, we can see that we can plot a signal where the time is even in the negative scale. So what does it mean to say that the time is in the negative scale? This is simply nothing but a representational view of the signal. So if somebody gives you the data about a signal, I start observing the temperature in this room from now on, and then I plot it across some t. Let's say I'm plotting the temperature now. This is time, and now let's say the temperature is 22 degrees, and then it increases to 24, and so on. So I've started observing it at some point t naught. So there is an originating point from where I start this observation. After that, I know what is happening, right? But even before I started observing, something was the temperature in this room. I did not know that, but there would have existed something, right? So how to capture that information in this representation? In order to capture the past, we say that whatever happened earlier before we started this observing, that will corresponding to negative time. So essentially nothing but we set the origin of this representation to be the point where we start observing. I'll say that the origin is t naught equal to some 0. That's the point where I started observing the signal, and this is all I know from my point of initiation, my point of starting. So something would have existed even earlier. Okay, what is that? That corresponds to the negative time. So this is all we'll say. So when you are plotting a signal, the time axis can be from minus infinity to plus infinity, and you can plot values even in the negative scale. So what does this mean? It doesn't mean that we know the past completely. No, it means that something existed in the past, and then we are just characterizing, or we are just plugging in that representation into the graphical form or into the mathematical form, so that we can characterize completely the past, present and the future of the signal when we represent it in the mathematical form. Remember, in the mathematical form, when I write an equation, we are saying that we completely know the signal. So which means we should know what happens to the signal at any point of time, which means we know what happens to it at time t negative, at time t positive also. So we should be able to draw what happens when it is negative time. So for example, let's take this signal. It says x of t is 2 cos pi t, which means I put t in the x-axis and I put x of t here. Then I can draw this signal not only on the right hand side but also on the left hand side, and so on. Okay. Now if I want to draw what happens to this signal, so this is t plus 3, it keeps on growing here. What happens to the negative time? I can continue and drawing this and representing it even for negative time. Similarly, this signal is just 1 for 0 and it is 0 elsewhere. So negative time is simply nothing but a representation of what happens to the signal in the past. That's all.